if you go to a restaurant with all your friends and you're not going to get seated until all your friends show up, if you have 5 friends, it's a short wait. If you have 100 friends, you might not get seated. And so every couple of years, the number of transistors has doubled, but also the number of chips has doubled. And so we ended up with so many chips, we couldn't coordinate them. And so what we've done is we've actually, analog to digital, digital to determinism. Determinism is what's next. It's what's going to allow us to have enormous numbers of chips working on problems quickly enough to give an answer and predictably and repeatably, just like with digital gave you predictable data, this gives you predictable performance.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. I hear about AI everywhere, but I've never stopped to think about running it on custom dedicated hardware built specifically for AI. I've always assumed a server farm or TinyML element. But today we're joined by a pioneer in AI-specific processing. Jonathan Ross, founder and CEO of Groq, has quite the background. He designed Google's first TPU, that's a tensor processing unit, and Groq's latest chip can do a petaflop, which is absolute insanity, but it's also incredibly useful, which is something we'll get into in a minute. So let's get right to it. Jonathan, thanks for joining me in the lobby today.
Thanks for having me.
How did you know that you wanted to be an engineer technologist?
So originally I didn't. I wanted to go into science. I wanted to invent new things. I started learning to program so that I could make my own video games, and I got feedback immediately, and I could learn I was doing things wrong, and I felt the improvement. And so I just wanted to do things that mattered and would have more immediate effect.
How much do you think video games plays into technology today in general? I hear that trend quite a bit.
I don't know. I stopped playing video games when I started to realize I had more fun programming than the video games. But I would imagine a very large number of programmers actually started off wanting to do their own video games.
I'm fascinated that programming was more interesting for you than video gaming. Can you expand on that a little bit?
So programming is much more high dimensional. So there's algorithms, there's actual fundamental things that you can learn that are applicable to the real world. And a video game, you're just shooting at things, you're solving little puzzles. They're very constrained. The programming is the whole world.
It's almost world building more than like being in the world then.
Yeah, and there's no limit.
But now you're doing hardware. How did you cross over the fence from software?
Good question. So I started off as a software engineer, and so the way that it happened was there was this team at Google that had trained this speech recognition model, and it was outperforming human beings. And I had a little bit of FPGA experience, a little hardware-ish, and there was no way to solve the problem in software. So I had to go a little bit deeper. And it's sort of like one of those things, as a software engineer, you might start off doing some web development, a little bit of JavaScript and so on. And eventually you get into like C++. And then if you get really gnarly, you'll get into the assembly. And then if you just go deeper, it becomes wires and it becomes transistors, right? And you just keep going. And at some point you're like, oh, this is crazy, but this is so much more fun.
What sort of problems can you not solve in software?
That's a great question. So the funny thing is, no one ever thinks of solving their problems with hardware. No one ever goes, my program my machine learning model, it's just not accurate enough. What I really need is better hardware. It just never occurs to anyone. But there's a bunch of fundamental problems, and they're way too technical to get into at the moment, that we can solve that turn into, we can actually make your models more accurate. We can actually complete them quickly enough that you can use them in real time. And we wouldn't be able to do that in software for the same reason that if performance matters to you, there's a limit to what you can do with Python.
As much as I'd love to poke on Python more, you mentioned machine learning, and that's an area where you and Groq really shine. Can you expound upon the work that you're doing there?
People often know that machine learning is important, but they don't know why. And the reason that it's important is it used to be that you could only solve problems where you had a procedure. If this happens, do this. Else, do this. And now it's probabilistic. Now it's like, if this thing is probably that, then you should probably do this. Otherwise, you should probably do that. And so what machine learning lets you do, is it lets you deal with uncertainty and to reduce the uncertainty in something. You can make more certain decisions, right? And what we've focused on is how to improve that certainty in machine learning, but also to be able to do it quickly. Because if you're responding to a user request, all that matters is how certain you can make something in that amount of time.
That might be the best explanation of machine learning I've ever heard. What don't people get about machine learning? What's the aha moment for people?
People don't realize quite how pervasive it is, right? It's used in almost everything. It's just become a tool in everyone's toolbox. On the other hand, people don't realize how primitive it is. Like if you remember when IBM first beat a human being in chess, everyone was like, okay, that's it, game over, machines are going to rule the planet. Um, and then when Google beat the human champion in Go, it was sort of the same thing. And there's just this whole series of things that we still need to solve. For example, machine learning models don't know how to set their own objectives yet, right? You have to tell them what to do. There's just a whole bunch of things that aren't yet done automatically.
So they're not necessarily coming up with their own ideas and replicating themselves to take over the world.
They're not deciding what to focus on. We're still telling them what to do. Now we could make mistakes in that focus, right? But they're not making their own decisions yet.
So we're still safe from the Terminator scenario. That's good to know. I want to dig into this more, but first I'm curious what it looks like to, and I quote, successfully drop out of college.
So I think if you want to be successful, then you need to drop out of college. You don't want to limit your earning potential, right? All the successful tech entrepreneurs have dropped out. That's the jokey way to say it. The reality is, as much of a joke as it is, I was working full time, putting myself through college, and the company that I worked for went out of business. And so I literally just couldn't afford to keep going to college, and I had to get a different job. But there is a tendency for people who are entrepreneurs to drop out. I think they get frustrated with how slow things are going. They're just like, let me just do things. And that's kind of where I was at with my life.
So what did you do then after you dropped out?
I joined a high frequency trading firm because they let me optimize things. Like any other company I would have gotten a job at, it would have been like, oh, just make this thing work. And here it was like, can you get this done in a microsecond? Yeah, what is a microsecond? Right. And that was fun. And then, of course, you come to this realization where, as much fun as it is, you're not having a huge impact. And you start to crave that. And then you start looking around.
What sort of parallels do you see in the high tech finance industry versus just the high tech industry?
Well, actually, interestingly, finance will often lead tech, and we get wrapped in our own bubble here in the valley. We think the Googles, Facebooks, Amazons, Microsofts of the world have all figured it out, and they're leading the edge. Most of the really leading edge technology is driven by finance. The network switches are all driven by finance. All this stuff is because they have the hardest problems to solve.
That makes sense. Yeah, I was looking at a network infrastructure that involved pieces of hardware I had never heard of before that were all FPGA driven. Packet timings were so important and latency was so important that it was literally driving FPGA development at the company for the finance space.
Yeah, we once had someone tell us that so if you think about a rack of computers, that the only slot in the rack that mattered to them was the top one because the amount of time that it took for the signal to propagate on the wire to the second highest server was just too long.
That's crazy. That's fascinating. There's got to be machine learning in finance too.
Oh yeah, it's all over the place. Everything. The sentiment analysis is a big one. So remember, in the short term, the stock market is a popularity contest, and in the long term, it's a weighing machine, right?
Sure.
And so if you actually want to do things that are high frequency, it's actually about human sentiment and what a human being is going to feel. Ironically, the faster you are, the more you have to understand humans as opposed to the actual reality underneath.
That makes a scary amount of sense, actually. Did you do any hardware in college?
So I never did that in college. I studied math and computer science. And then I worked for that finance company. taught myself FPGA development. Actually, I got the job sort of mistakenly. They thought I knew what I was talking about, and so the CTO of this financial company was interviewing me, and he was leading me to a solution for his problem, which he already had in mind, and it was FPGAs. And as we were getting towards it, I actually didn't know what an FPGA was at the time. I ended up spending years programming them, but as we got really close to it, I had just happened to have been playing this online flash game called Engineer the People, where you design circuits, literally a week ago. And I made a comment, the hard thing is making timing. Now, what that
Hmm.
means, I'm not going to explain it. It's not relevant. It meant something very different to anyone who knew what they were doing than what I thought it meant. But he thought I knew what I was doing. And so he hired me to do it. And then I had to figure out how to program FPGAs.
We'll find out how that story ends in just a moment. Moore's Lobby is sponsored by EBV's podcast, Passion for Technology. Ready for the next level of optimizing your ears? Techies rejoice. The new Passion for Technology podcast is dedicated to the latest technologies, trends, and applications in the electronics industry, such as a podcast series on analog and power management. There are already 3 episodes up now and 3 more coming soon. Listen also to recent episodes on silicon carbide and gallium nitride, wearables, EV charging, UV LEDs, edge computing, and robotics. Tune in now and dive into the world of semiconductors. Find it on all major podcast platforms. Enjoy. We're back with Jonathan Ross, founder and CEO of Groq. Jonathan, you were just telling us you got an FPGA job but had no idea what you were doing. Were you in over your head? Like, what was going through your mind?
I think anyone who does anything interesting has to enter it with a little bit of naivete, because if you knew how hard it was going to be, you wouldn't do it, right? And so one of the advantages that I had was I didn't realize how difficult it was going to be. It literally took, I think it was 4 months from when I started to have the first like LED blinking on the FPGA. But then a month later, we had it processing Ethernet packets. So there's this
Hmm.
huge learning curve to just get started. But once you were there, you could do things really quickly that would have been impossible in software.
Almost like once you knew how to blink a light, you knew how to decode packets, but getting to Blinky was the hardest part.
Yeah, exactly.
Did you fall into machine learning, or was that on your radar, or how did that whole thing start?
So, interestingly enough, I had this view that anything that was probabilistic wasn't interesting. I loved theoretical math, proving things, and all this. I had no interest in probabilities. And I was at NYU, and I ended up taking a course by Jan LeCun. Now, quite famously, one of the leading, it won the Turing Award. We were in his class, and I started getting sucked into the machine learning. He happened to teach us about these convolutional neural nets and other things that at the time there were no textbooks on. There was just nothing about it. It was a waste. It was still part of the AI winter. And I ended up later on getting a job at Google. And one day I got an email from Andrew Ning, also fairly famous. And I had been doing this hardware stuff at Google for machine learning. Jan LeCun was asking for a grant to do hardware stuff, and they're like, "Oh, you're doing that. You're an expert. So why don't you sponsor the grant?" And so I got this grant from Jan LeCun, this request, and on the form it was, "Is there any reason why you'd be biased?" And I'm like, "Yes." Jan LeCun did not turn in my grade, but you should still give him the money anyway. And so he ended up getting the grant, and we started recommunicating. And so I started looking at machine learning again and how to apply it at Google. And what had happened was the speech recognition team at Google had just had a major success. And so Jeff Dean, the most senior engineer at Google, actually was putting together a presentation for the leadership team, and it was just 2 slides. The first slide was good news: machine learning finally works. We have a speech recognition model; it outperforms human beings. Slide number 2, bad news: even though we're Google, we can't afford it. We would need to double or triple our global data center footprint, right? Something on the order 20, 40 billion dollars. And that's for speech recognition. If we want to do anything else, it's going to cost more. And that was called a success disaster. And again, jumped in over my head. I started a 20% project at Google. You're allowed to spend 20% of your time doing anything you want that might help Google. I happen to often have lunch with that speech recognition team in New York. They needed help. I'm like, okay, FPGAs, machine learning, I've got this. Started working on it. It took like a year to turn it into a real thing, but it got approved, and we started doing things at Google with ASICs.
Yeah, so ASICs almost seem like a logical progression from FPGAs, where if you know specifically what you're doing, you just make the chip itself.
Yeah, we just didn't know what we were doing. That was the one part we skipped. We figured it out
Uh,
though.
I'm latched onto your words success disaster, and I think that might be my new job title. It's walking success disaster.
Well,
Uh,
what it meant was there was a success in that machine learning finally worked, and we were headed for a disaster because we couldn't support it in production. There weren't enough machines at Google.
no, it makes sense. It's like, oh, we have the answer, but it's out of reach.
Yeah,
Can you define some machine learning terms I hear thrown around a lot? I hear tensors, TPUs, neural networks. Can you just kind of touch on some of those things and what are they and why are they relevant for machine learning?
sure. So tensor is a math term which, because it sounds cool, started to get thrown around. There are mathematicians who will say these aren't really tensors, and then others will be like, yeah, it kind of is. It's just a cool term. And what it's come to mean is there's a thing called a matrix. It's a two-dimensional set of numbers. It's like if you're used to spreadsheets, like just imagine a two-dimensional grid there filled with numbers. It's a matrix. And if you make it more than two-dimensional, then it's a tensor, right? And so in machine learning, you're working on these high-dimensional things, and therefore they're called tensors. Sounds super cool. So then they also came up with TensorFlow, which is the framework at Google, which sounds super cool. And now everyone's using the word tensor everywhere. And TPU is Tensor Processing Unit. That's the chip at Google, the effort that I started. And it was not called that internally. That was the name that was applied much later, and I like it much better than what we were calling it before.
Can you share what it was called internally?
Yeah, it was actually called C Star.
Okay. It's not as cool.
Yeah, and before that, it had another name. It was Squirrel Brain, and before that, it was actually called Superfluid. And so it had a whole progression of names until we eventually got TPU.
Okay, fair enough. TPU sounds official. The other ones sound like branding names or engineering project names.
I don't know. Squirrel Brain was. I didn't come up with that one, but
That's a
that
good
was
one.
terrible. That was
That's good.
terrible.
Yeah, you can't pitch that to like shareholders or investors.
Yeah.
Can you tell me more about the Moonshot factory?
Yeah. So I spent a little time there. What's interesting about it, I get to work on bio, I get to work on mechanical engineering, and fundamentally, what they're trying to do is, completely open greenfield, come up with ideas for new $10 billion a year businesses. No big deal. Just as an FYI, NVIDIA is a $10 billion a year business, right? So that's the scale that they're aiming for. And a bunch of the things that I started while there, I was in the group that came up with the ideas. And a bunch of the things I can't talk about because they're either still going or they haven't, talked about them publicly. But what was really interesting was, what do these businesses have in common with each other? What does it take to build a $10 billion a year business? And so we spent a lot of time on that. And then the thing that I find most fascinating about the Moonshot Factory or Google X, you now hear all these like X Labs or company name X, and it's like propagated throughout tech.
SpaceX.
Well, I actually, fun fact. So when the whole renaming thing happened, Google X wanted to be renamed X, just X. Turns out Elon Musk owns X.com and wouldn't sell it.
Fascinating.
Tried to buy it, but he would not sell it. So, so I think he was probably thinking SpaceX or something along those lines well in advance, or it could have been when we asked to buy it that he had the idea. I have no idea.
Interesting. Okay, so tell me about the Moonshot Factory. So your job was to try and come up with $10 billion ideas.
Per year, per year.
Is that stressful?
Well,
What's that like?
um, it was a little bit like retirement.
Hmm.
There was no accountability response. It was so far away. So when you start a startup, you're just trying to get to default alive. You're like, you've given me some money, you've entrusted me. Now I want to give you a return on your profit and I want to iterate. And there's this saying that I really like, which is the speed of iteration is the speed of innovation. And if you're not getting any feedback, you don't really know whether or not you're making progress. And when your goal is a $10 billion a year business, you're not going to know whether you're on that track until you're very far along. And so we built all these very successful technical projects. And I got to a point where I'm like, we keep getting these things to a point, but it doesn't feel like it's the whole thing. Like when starting TPU, it was there was a problem, a user need, and we went to solve it and we solved it and we solved it quickly. And then it started to become valuable. And I think most successful things, they don't start off with, I want profit or I want to make a whole bunch of money. They start off with, there's a real customer problem. We're going to go solve it and we'll figure out how to monetize it later.
So how'd you go from a job that you describe as basically retirement into doing chips again?
So actually, interestingly, I was done with chips. I did another thing with chips and I'm like, okay, this is it. I'm done. But I had so much experience now with these other things, biomechanical engineering, and none of them had the high dimensionality of working with chips. When you're working with chips, it's everything from the device physics all the way to category theory. It spans it's like manufacturing and design. It's people leadership and it's engineering. It's everything, right?
Yeah.
And I just couldn't get that full exposure from anything else. And so we were thinking more along the lines of machine learning, but when we started meeting venture capitalists, all they wanted to know about was this TPU thing because it had actually just become public recently. It hadn't been around that long. And they just kept asking questions about it. And one of the questions is, well, what do you think the problem is that should be solved? And I'm like, they're hard to program. And I include TPU in that. TPU is very difficult to program. I literally designed the first TPU, literally implemented half of it by area, by lines of code, whatever you want to count, like half of it. I was a software engineer and I couldn't program the thing. Like, they had dedicated people programming it. So it was difficult, right? And GPUs, by the way, are worse. They have all these tricks to make it look easy to program. But under the hood, like the people that we were hiring were like, yeah, GPUs are worse. And so as we were talking to VCs, and this just became a theme, like anyone would ask, I'd be like, that's the problem. I'm like, okay, let's go solve that. And so we actually spent the first 6 months working on the compiler. We forbid ourselves from thinking about what the chip architecture would be. We had no idea, like literally none. And the analogy is if you're going to design a car, do you want to ask a bunch of mechanics what that car should be like, or do you want to ask a bunch of drivers?
Let's let that analogy compile for a moment. We'll be right back. Moore's Lobby is sponsored by EBV's podcast, Passion for Technology. Are you ready for the next level of optimizing your ears? Techies rejoice, the new Passion for Technologies podcast is dedicated to the latest technologies, trends, and applications in the electronics industry, such as a podcast series on analog and power measurement. There are already 3 episodes up now and 3 more coming soon. Listen also to recent episodes on silicon carbide and gallium nitride, wearables, EV charging, UV LEDs, edge computing, and robotics. Tune in now and dive into the world of semiconductors. Find it on all major podcast platforms. We're back with Jonathan Ross, CEO and founder of Groq. Now, I gotta ask about the name. I absolutely love it. Can you tell me more about it?
Well, and if I recall correctly, you talk about grokking things in your LinkedIn profile.
Yes, I think I do.
Well, what it means is to understand something deeply and with empathy. And where the empathy part comes in is innovation has this connotation. And remember, Google X, we were all about innovation. That's what we spent all our time thinking about. And at the beginning levels, when you're first learning how to innovate, it's like, okay, come up with good ideas, right? Let's be creative, just freely associate, right? And then as you start progressing, it becomes about the management side. How do you actually get people to adopt crazy ideas, right? This is where every movie about an innovator breaks down. It's the part where they're trying to convince other people and then they become shells of human beings as they fail to convince people. And so it's change management. That's all it is. as an industrial effort, as a team effort. And so the missing ingredient in innovation is actually empathy,
Hmm.
because you can't communicate to other people. You can't get another human being to change something that they fundamentally believe in unless you have empathy and compassion towards them. And so Grok is the perfect name for an innovative company.
And it comes from the Robert Heinlein novel Stranger in a Strange Land, where it was
Yeah.
like an alien coming down and they're trying to communicate and
So
understand.
so it's also entered the lexicon, right? People just
Yeah.
say it. It's on your LinkedIn profile, right?
Yeah.
And so the concept is really the important part. And so we we understand things deeply with empathy. That's Grok.
So why did you leave Google to do this?
I first left Google and joined Google X. They're separate,
Okay.
and I think that was fascinating, and it was most of what I wanted. And I strongly recommend, if Google X ever offers you a job, take it. It's a great journey. You'll learn a lot. But as was mentioned to me when I was joining, people don't stick around there very long. They like entrepreneurs who are going to go off and do other things. That's part of the positive part of the culture. They don't consider lack of retention a problem. They consider it success because they're hiring entrepreneurs who are not going to be sticking around very long, right? But that sort of lack of accountability really nagged at me. And I think a lot of the entrepreneurial folks, at some point, they're like, I just want to actually do something. And I felt like I got to do a bunch of interesting things, but nothing was going all the way. And I just had to take something all the way.
It's almost like you successfully dropped out of college and then you successfully dropped out of Google.
That's right. And actually, I have now been at Grok longer than anything else that I've ever done.
Well, it seems to be working. Can you tell me more about some of the technical feats and things that are really you're excited about in the industry and at Grok?
Yeah. So if I was to go back to that explanation of machine learning, right, reducing uncertainty, one of the really interesting things about our chip is that it reduces uncertainty in a lot of ways. The numerics are more accurate, so you don't have as many problems. Like, computer scientists view the numerical aspect as just like it's a fact of the world. You can't make the numbers better. In fact, everyone's going to these lower accuracy numerics. We actually made these super, we call it true point because it's floating point that actually gives you the correct result. A wild concept, giving you the correct result. But that's the thing, people become habituated to their world. They don't realize how things could be better,
Hmm.
right? It's like, this is the way they are. And we just want to be like, this is the way they could be. And another one is, when you're using any one of these chips, like, a lot of people still use CPUs. They don't even use GPUs. Everyone's like, oh, GPUs are what you use for machine learning. Yeah, maybe to train, but this is going to sound weird. GPUs are actually too slow. So there's two types of speed. There's how long until I give you an answer, and there's how many answers I give you every time I give you an answer. Even if it takes me a long time to give you an answer, if I can give you a large number of answers, it feels fast, right?
Sure. Parallel versus serial, right?
Exactly. That's exactly right. Parallel versus serial. Now, if I'm giving you a large number of answers in parallel, that works great for training. But for inference, for taking the model and actually using it in the real world, right, to answer a web query or to control a drone or a car or anything like that, it's not just how many answers I give you, it's how quickly you get the answer. Think about it this way. Imagine for a moment that you're wearing VR goggles and that there's a knob that allows you, and all you're seeing is the world in front of you. And you can set a delay from between 1 second and 3 seconds, right? And let's say at 1 second, I throw you a ball. Okay, maybe you can catch it, maybe not. But at 3 seconds, you have to predict that I'm even going to throw the ball,
Sure.
right? You have to look at my body language to figure out I'm going to to even catch it, right? That's ridiculously complicated.
Yeah.
So the faster you can make these predictions, the easier they become. So again, it's about reducing uncertainty. So we need to give speed. So people still use CPUs because they take less time to give an answer than a GPU, but they give fewer. And what we've done is we've actually built a chip that does both. It gives you the answers quicker than even a CPU does, but it actually gives you the throughput or the parallel performance of a GPU or better.
How fast is it?
So our chip can do a petaop. A petaop is 1 quadrillion operations per second. That's four commas, not three.
Yeah.
Um,
Whew. Okay.
yeah. And the most amazing part was we achieved that on an older technology, right? We didn't actually have to go to TSMC, who's leading in fabrication. We actually used Global Foundries, which is fabbed in the US, and we're still able to get a Petaflop, which is the fastest chip ever built on an older process. And that's because the architecture and the software are where our performance comes from, not the transistors themselves. We use the same transistors as everyone else.
I've heard that it's 300 times faster than NVIDIA. Is that true?
So
Can you go on record?
I can go on record. So let me explain. So they were doing some drug discovery with our chip at Argonne National Labs, and they compared us, all the other startups in the space, NVIDIA, everyone. And what happened was, versus what they had been using, the V100 GPU from NVIDIA, we were able to produce answers 200 times faster, both throughput and latency. Both were 200 times faster versus the A100, which is their newest one. It was 330. Or sorry, the first one was 333x. The older one, it's 200. Now, of course, NVIDIA can't go, no, you're only 200x faster, right? It's not
Right.
a correction they want to make.
You're using the same transistors, going through global foundries, using established your manufacturing techniques. Is it then in the architecture that's making this work? How is this happening? It sounds too good to be true.
So you could say the same thing about a GPU then, right? Like if all you'd ever seen were CPUs and someone came along with a GPU and said, hey, I can make this thing much faster throughput wise, you'd be like, that sounds too good to be true. But once you understand how it works, it's like, oh, that's obvious, right? I've got more but wimpier cores. What we did was very different. We actually, and this is really stretching the understanding, there was a point at which we as human beings moved from an analog universe to a digital universe. There's actually a time before you could actually have records that lasted forever. Like things were on paper, paper deteriorated. You assumed, like, there's a comedian who jokes, everything that I did in high school is just rumor. You have no idea, right? Because it was before social media. And so we moved to digital. But the thing is, what powers improvement from computation is performance. And performance has steadily improved. And whereas moving from analog to digital gave you permanence, things could now exist forever and you could keep a copy. What didn't happen was the ability to accurately reproduce performance. And so you had these data centers with tens of thousands, hundreds of thousands of chips in them, and they were completely out of sync with each other. And why that matters, it's like if you go to a restaurant with all your friends and you're not going to get seated until all your friends show up. If you have 5 friends, it's a short wait. If you have 100 friends, you might not get seated. And so every couple of years, the number of transistors has doubled, but also the number of chips has doubled. And so we ended up with so many chips, we couldn't coordinate them. And so what we've done is we've actually, analog to digital, digital to determinism. Determinism is what's next. It's what's going to allow us to have enormous numbers of chips working on problems quickly enough to give an answer and predictably and repeatably, just like with digital gave you predictable data, this gives you predictable performance.
Can you define determinism for me?
Yeah, it's giving the exact same performance every single time. So
Okay.
imagine if you asked someone to do a task and they said, I will have that done for you in 15 minutes, 37 seconds, and 619 milliseconds. That would be useful to know, wouldn't it?
To a point. Yeah.
Well, I mean, like, it's certainly better than I don't know, right?
Yes.
Exactly. And when you compile software today, it's not deterministic. You actually just have to run it 1,000 times and take
Yeah.
the average, and that's how fast it is. When you compile something for our hardware, we'll tell you this is going to run for 47,517 nanoseconds, plus or minus zero. There's no variation.
That's incredible. That's almost like quantum, where you kind of have things going and then it all lands on the answer all at once.
Well, quantum's a whole other can of qubits, and I think we can avoid that one here.
Fair enough. One of the claims on the Groq chip is that it corrects single bit errors in hardware. Can you tell me more about that? Because that sounds fascinating.
Yeah, so People have corrected errors in memory for a while. If you have a gigabyte of memory, you get about one error in it. I think it's per month or week on average. I forget the exact frequency. So that means that when you've got a mobile phone and it stops working, sometimes it's because one of the bits in the memory just flipped. There's no correction on it. Mobile phones don't get that. Servers do have that because you can imagine if you did a financial transaction and one of the bits flipped, it might be a bank error in your favor, it might not, and they don't want that, right? What's happened is we now have so many chips in production. There's so many of them. Like, we're building gigawatt data centers now. That's powering millions and millions of cores. And so you get these bit flips in the chips, and they're really hard to track down. And so, since we have experience with a much larger scale of deployment, then the hardware companies, they don't think, again, it's the mechanic versus the driver. They're like, hey, the customer asked for this, I'll give them this. They're not thinking, oh, yeah, like we're going to deploy a million of these, so all of a sudden we get a million times more errors. And so we realized that we were going to have to start correcting errors on the data paths in the chips. Otherwise, the number of errors would be too great and people would start seeing them. So it's about reliability. It's about being able to depend on your chip giving you the correct answer.
So basically, minor errors are not a big deal until you scale it up and minor errors start to really add up into something that's noticeable and a big issue.
Yeah, if you have a million chips, you have a million times as many errors as you had before.
So how do you fix it in the data path? What do you do?
So you do error correction. There's all sorts of techniques for this. The standard is something called Hamming code distances. I'm not going to get into it's way too technical, but it's really the same technique that's used on memory, but we do it on the data path. And there's reasons why this is very difficult to do in a chip as opposed to in the storage. But there are things about our architecture that make it much more amenable to corrections.
I feel like this is circling back to that timing conversation. I've seen the timing charts of some of the chips where I work, and it's a it's a puzzle for sure.
Well, no puzzle with ours. We just tell you at compile time, and there's no variance. We're just fundamentally trying to make it more predictable, right? We're improving the certainty.
What industries and what areas are most interested in that certainty? Where are you seeing people get really excited?
We talked a bit about finance, and in finance, it's if you're doing something real time, you have to get it done in time, and very competitive. Some of the jobs are very large, and so they need an enormous amount of compute. And what we're seeing a lot is there is the real time component, sentiment analysis, and all that, but really the bigger problems are there are jobs that will use entire data centers worth of compute, and they'll take a weekend to run, and they really need the answers faster than that. And it's not very productive for the quants. They want to be able to get answers, before they get a coffee or in minutes, right? And so the speed of iteration is the speed of innovation. Another one is autonomous vehicles. So you can imagine instead of it being hours reduced down to minutes or days down to hours or minutes, they have to decide whether or not something is a person or a shadow in milliseconds. Otherwise, someone could be injured. And so having determinism is super important for them because they can know that they're going to get the answer in an exact amount of time and make that decision. It just removes that uncertainty from how they're programming. And so we've had a lot of pull from the autonomous vehicle industry.
That would really impact the entire design from the asphalt up, knowing how long it's going to take to get certain things, to get certain answers.
And control theory, which is the discipline around this, is heavily in like a large portion of it is what do we do with the uncertainty, and we just take all of that uncertainty out and make it
Yeah,
much simpler, right?
yeah.
And then, drug discovery, like ever since we published that result, we've been inundated by a whole bunch of companies that have wanted to use our chip. And actually, one of them is getting free compute. It's being like they're even paying for the energy from one of the large companies. And they're like, yeah, but it's slow. Like it doesn't matter if it's free. I get my answers 100 times faster from you, and that's worth a lot more, and I'll just pay for it.
That's the $10 billion a year business right there, is something that was free, but it's so much better that they're willing to pay.
Exactly.
Have any use cases surprised you? They just came out of left field and you never saw it coming, but it's been a winner of a solution?
That's a good question. We've been surprised by a lot of things. We didn't realize how much of an itch that we scratched with this design. I mean, we had a couple of use cases in mind, but it scratched a lot. One of the more interesting ones, nuclear fusion, very important, kind of science fiction-y, but people are making progress. They're getting pretty close to getting more energy out than they're putting in. They just keep, the speed of iteration is the speed of innovation. They keep getting closer and closer and closer. And so we're working with Argonne National Labs, and we have this great partnership with them, and they're doing some really advanced stuff. And they had this, fusion reactor control loop, and they were trying to control it with GPUs. And this thing, like, this is a huge machine, but when it gets out of sync, like, it comes off the floor, and you can see people's shoes under it, and it comes crashing back down. And their tolerance is they have to have an answer in an exact amount of time, like a millisecond. And if it's late, it could destabilize the magnetic field. And so they've tried everything. They've tried GPUs, CPU, everything, and nothing is fast enough. And so GPUs, for example, they can only get down to 3 milliseconds, but then they only get 300 outputs in that time. And we were able to get it under 1 millisecond and produce 600 times as many outputs as the 300 in that same amount of time.
Wow.
Yeah, all sorts of use cases like that we just never envisioned when we built this chip. And the funny part about it is if you look at the end user license agreement for an FPGA or other chips, it often says you cannot use this to control a nuclear reactor. Now, I never thought in a million years people would actually try to do it, but they are.
It's in the why?
I guess they don't want the responsibility.
Well, I guess there's not a lot of upside for them.
Yeah, whereas we're just doing all these cool things. And like one of our engineers who joined recently, they did a post, and it was like in their first couple of months at Groq, they worked on autonomous vehicles, they worked on nuclear fusion reactors, drones, and other things like advertising and whatnot, but a bunch of cool stuff as well in just a couple months.
That's incredible. What has surprised you about Groq and your experience in the marketplace?
I think the biggest one is, and I think this is true for every single startup. You have a great solution in mind. You actually know a customer pain point. You have a solution, and you walk in and you're like, determinism, and they're like, so? You're like, determinism, and they're like, yeah, I gotta go. And what you're not doing is you're not connecting it to their need. It's about pain points, and a better way to do it is to be like, okay, I understand your problem. Your problem is you think you don't have enough label data because you're not getting enough accuracy, right? Yeah, exactly. And then you're like, but if you had a larger model that could make up for that, right? Yeah, that would work. Okay. And the reason that you don't have that is because, well, we couldn't run it in production. It's like, oh, okay. So if we were able to run a larger model in less time, and we don't have to margin it because it's deterministic. We don't have to like have it be twice as fast as the worst case. So on average, it's good, right? That would actually help you build a bigger model and be more accurate without having to get more data, right? Yeah, that would be awesome. Do you have anything like that? Yes, we have hardware that does that, right? And so I think the surprising thing has been what should have been obvious, and I think every founder learns this, which is you're living and breathing this stuff, and the solutions are obvious to you, but you have to put it in a way that the customer can understand it. And once they do, then it starts selling itself.
We'll be right back with Jonathan Ross. Moore's Lobby is sponsored by EBV's podcast, Passion for Technology. Are you ready for the next level of optimizing your ears? Techies rejoice! The new Passion for Technologies podcast is dedicated to the latest technologies, trends, and applications in the electronics industry, such as a podcast series on analog and power measurement. There are already 3 episodes up now and 3 more coming soon. Listen also to recent episodes on silicon carbide and gallium nitride, wearables, EV charging, UV LEDs, edge computing, and robotics. Tune in now and dive into the world of semiconductors. Find it on all major podcast platforms. And we're back with Jonathan Ross. What sort of culture do you have to build at a company if you're doing something totally new like this?
I could probably geek out on this more than all the other stuff we've talked about. When I started Groq, I thought it was all about the technology. I'm like, product, technology, technology, technology. And then you start bringing people in and you're in the trenches together and you're like, wow, this is just as interesting. And so I think the best companies balance product and talent. The better the product, the better the talent, the better the talent, the better the product, right? Because the best talent wants to work on the best products, and the best products are built by the best talent. The thing that we live by is something we call talent density, which is it's not just about hiring well, it's also about not hiring poorly. Every single hire matters. We actually, in our most recent all hands, we talked about the woman. She started as a receptionist at Groq, and she was instrumental in getting our first servers delivered to our first customer. And she acted like a leader in the process. She made her own decisions. At Groq, everyone is a leader. We do not hire people to follow orders. There's no one who's just doing what they're told. Everyone has to think. And it's really about who you get to work with. That's the most exciting part.
What's the competitive space like? Are there other companies trying to do this too?
Okay, so I mean, if you're building a business, there's an element of competition. I think when you start a startup, you first have this level of paranoia where you're like, ooh, if I talk to a VC and I tell them my ideas, they're going to copy it. VCs get so many pitches that they could care less, right? Like they're not going to steal your ideas. And then every single startup that pops up that's sort of adjacent, you're like, they're copying us. They're doing something similar. And then as you start to get used to it, you're like, oh, what they're doing is so different from what we're doing. Like they may think they're competing with us, but we don't actually consider them a competitor. And we've actually had a bunch of startups that asked for conflict, to waive conflict from the VC. And we're like, sure, they're not competing with us. And they're like, really? And I'm like, they may think they are, but they're not. So if you look at the market, it's like there's data center, there's mobile, and there's IoT, right? Or edge mobile. And then within those, there's a bunch of differences, right? So for data center, training versus inference, right? Within them, there's only a handful that are funded well enough to actually compete. And you start off with like 100 startups in this space, and there's maybe one or two that are sort of in the same actual bucket. And then when you really look, you're like, oh, those are hardware companies. They're not like starting with the end user in mind. They're like building an engine and trying to like get people to drive it, right? They don't. And so like we started with software.
They know how to build a chip.
Yeah, exactly. And so, if you going back to what we said earlier, no customer ever goes, what I really need to solve my problem is hardware. It's always the software. And so we started with the software. And so it's all very different. The only real competitor that we have is some of the large companies like an NVIDIA and those sorts. And even there, we're focused on those areas where we're getting like 100x or 10x, right? It's not close. And so in a large way, even that is different.
Well, that's a great place to be. And while we're talking about hardware solving problems, what would you say to hardware engineers that feel like software is maybe taking over?
So I would say we've been walking through a time where hardware engineering, electrical engineering has been on the decline. And so I think the hopes have been low. But to all you electrical engineers out there, just remember, keep your hopes active low, and it'll all be good.
Have good grounding.
Stay grounded, my friends.
Okay, lightning round. If you weren't doing what you were doing, after this conversation, I think maybe there was only one path for you ever, but what would you be doing instead? Would you like run a surf shop in Hawaii or something?
So that's an interesting question. I never, ever imagined being a CEO. It never occurred to me. And I actually became the CEO after starting Grok. It wasn't even day one. And there was someone else I wanted to be the CEO, and we actually wrote down the responsibilities of my job and their job. And what I wrote down was things like I want to focus on the culture, on the talent, on these other things. Yeah, the engineering too, but all of that. And that other person said, you just wrote down the job of the CEO. And I'm like, no. And they're like, yeah, you did. And so I ended up becoming CEO because the things that I liked were the things that CEOs did. But I lucked into that. I just never imagined that CEO was the thing that would allow me to do all the things that I like.
So you almost successfully dropped out of like R&D to CEO.
Exactly. Yeah, fail your way upwards, right?
What are your most favorite and least favorite instances of AI in pop culture?
There's an interesting dichotomy between Eastern and Western cultures where, like, for example, in Japan, robots are going to save the future. And here in the United States and in other places, it's like, oh, Terminator gonna kill us all. It's the end. It's a technology, and with all technology, we need to be wise in how we use it. But what it's going to allow us to do is also amazing, right? We need to embrace the change.
I love ending on a positive note. Jonathan Ross, founder and CEO of Groq, thank you so much for being here today. This was a blast.
Thank you. Thanks for having me.
And that's it for today. If you want to keep digging into this, check out Groq Day on March 31st, a virtual event for enthusiasts and early adopters of AI, ML, and high-performance computing. You can sign up at groq.com/events. And if you enjoyed this podcast, let us know by leaving a review. And if you do, tell us on social media because we're sending out some mugs and stickers to show our appreciation. I'm your host, Daniel Bogdanoff. Thank you for joining me today in the lobby, and I'll catch you next time.